Hello everyone. I wanted to just make a really quick video on how to go about tackling buoyancy problem, a little bit of a refresher from physics as far as what we define buoyancy force as, and that sort of stuff. So getting right into it, buoyancy is a resultant force of a displacement of a liquid or a gas from a solid. So for example, if you have some container filled with a liquid, and you are putting some solid into this liquid is going to be displaced a certain amount. So the displacement from this liquid is going to result in a net force opposite of gravity that we call buoyant force. Call that FB. So this buoyant force is opposite of gravity, and it's equal to the amount or the weight of the fluid that's being displaced by the solid. So, for example, we have one cube here, length L. The force of buoyancy generated on the cube is going to be equal to the weight of the water that's being displaced. So, the weight that's being displaced. So how you go about calculating that or figuring that out, the force of buoyancy is equal to the density of the liquid, so whatever the density of this liquid is, times the volume that's being displaced. So here the volume being displaced is going to be L cubed. If this is a cube with equal sides of length L, the volume that's going to be displaced is going to be the volume of the cube. C for volume of the cube. Now, density times volume is going to give you mass, so you have to remember to put on the gravity term so that you end up with a force value. So, key things to remember, buoyancy is going to always point opposite of gravity, it's always going to point up. The density is going to be the density of the liquid that the solid is submerged in, or liquid or gas, so technically the fluid. It's going to be the density of the fluid times the volume that's being displaced. So you're kind of mixing it up here. It's going to be the density of the fluid, but it's going to be the volume of the solid. And then you have to multiply it by gravity. So it happens with liquids. When you go in the ocean, you feel lighter. You can feel yourself being buoyant. That's an example of buoyancy force for a liquid. As you are around in the atmosphere, the air around you is also applying a certain amount of buoyancy force, but the density for the air is much lower than the density of salt water, which is why there's not that much of a buoyant force acting on you at all times. So let's get into this problem that we discussed in class. The problem is broken up into two parts. Part A is asking you to figure out what is H, at what height or what depth is the tank going to be submerged if it's just under equilibrium conditions. And part B is what force applied needs to be added such that the top of the surface or the complete tank is submerged. So let's go about doing that. Let's focus on A first. So for A, we have this tank. Imagine right before the tank goes in, you have some volume of the tank, which is filled with air. You have some pressure, which we'll say P naught, which we'll just say is ATM. And then what's going to happen next is you are going to let it just settle out. So the tank's going to decrease. Going to reach equilibrium, and some of the water is going to go into the tank. So what we have here is, if we just label it, this is length L, it's the complete length of the tank. The problem statement has this labeled H. So we said buoyancy is a force, so let's start with the free body diagram. So we have our weight from the tank pointing down, and we have our force of buoyancy pointing up. It's not accelerating, so we know that the summation of forces must equal 0. As such, the force of buoyancy must be equal to the weight of the tank. So, figuring out force of buoyancy, like we said earlier, is equal to the volume, the density of the liquid times the volume that's being displaced times gravity is going to be equal to your weight of the tank. So figuring out the volume being displaced is going to be key here. So the volume being displaced is not this whole volume right here. It's not that whole volume because some of the water is rushing into the tank. The volume being displaced is actually here. Just this area. So in order to figure that out, we need to introduce a new variable which we'll call y. So rho of the liquid, which in this case is water, times the volume of this tank is cylindrical, so it's just going to be the bottom area, times the y term times g is going to be equal to the weight of the tank. So from there, algebra, you can solve for y, and you can get the height, the amount of water that's being displaced that's contributing to your buoyant force. That's going to come in later because, as you can see, there's this extra term here that's missing. H is composed of y plus some other variable. So in order to find that, we need to figure out what's this volume, what's this change in volume going from normal to now this new condition. So that's going to borrow a little bit from, if you remember, from chemistry or physics. We're going to treat this as ideal gas, so you're going to have pressure in 1 times volume 1 going to be equal to pressure 2 volume 2. Okay. Now the initial pressure 1 is just going to be atmospheric, which I'm calling P naught. The volume initial is just going to be the total volume of the tank, but right before the tank hits, once that tank hits the contact of the water, all the air that's in there is going to be at 14.7 psi, and none of the air molecules are escaping or anything like that. And then that's going to be equal to this new pressure within the tank. So the air pressure within the tank is going to be greater because you have less volume, and this new V2. So figuring that out, we have P naught. Volume is going to be the surface area times the entire length, which we're going to call L, which is given in the problem statement, plus equals this P2. This new volume is going to be the surface area times this term right here. So it's this whole length, which we don't have written, which I'll just call L, little l for now. Little l. The a's will cancel, and we'll have that P naught L is equal to P2 little l. So we need to figure out what P2 is. P2 is the pressure within this tank. Now it's acting all around. I'm going to just erase some variables. The pressure in this tank is going to be acting everywhere, as we discussed in class. The pressure in a gas acts all around, which is even going to act right here at this interface. So this interface is P2, which we have a continuous same liquid going all the way through around here, so it's also going to be the same as P2 out here. That's going to be where the hydrostatics comes in. So that pressure is going to be just this height from the water plus our P atmospheric. So you can say that P2 then is equal to, going up from the bottom up as we discussed in class, rho G, but not H. In this case, the H is going to be what we call Y. Y plus our P naught, which is PATM. So if we plug that into here, we can figure out what Y was from the previous part. Then from there, we can figure out what our L is. And from there, it's just a matter of figuring out what this new, what this little portion is right here. You can say that once you figure out L, you take big L minus little l, you'll get this new, I guess we can call that T, you'll get that new dimension T, and you can add that to Y and figure out what that H is, or any other type of algebra or fancy stuff that you feel like doing. So that's part A. For part B, it's not too bad. So part B is saying you have a tank here, and now the next thing that you're doing is you want to figure out how much force do you need to apply such that the tank is fully submerged. This is our water. This is our P1 again. This is our PATM. Call it P naught. This is our new volume, and this is a new P2 within the container. So again, we're going to do a free body diagram. So if we are looking at the tank as a whole, and we're doing a free body diagram, we have that weight of the tank, plus we have this force applied, and it's being counteracted on by this buoyancy force. Okay. Now, it's not moving, so we know that the summation of forces is equal to 0. So you know that the force of buoyancy must equal the weight of the tank plus this force applied. Now I'm going to just shift this over here. Force of buoyancy is going to be equal to rho times g times the volume being displaced. Now the volume being displaced is this entire area right here. It's the leftover air within the tank, the trapped air. So that's going to be volume displaced is equal to the tank minus force applied. We've got to introduce some variables. We'll call this y. So that means that the force of buoyancy is equal to rho g surface area times y equal to all this stuff. Okay. Now we have one equation, two unknowns. We can't solve that yet. So we need to go back again to our P1, V1. Again, this pressure is going to be applied in all directions, including right here. And just using the exact same concept, we'll be able to introduce a new equation and solve from there. So P1, V1 equals P2, V2. PATM times volume total is going to be equal to this new P2 times this new V2. I'm going to delete that. I'm going to cancel out the area terms automatically. So this is going to be just big L is equal to P2 times now the volume of this container. When we say V, we want this whole V right here. That's going to be equal to area times Y. But I canceled out the areas, so it's just Y. Now it's just a matter of figuring out what our P2 is. Again, P2 is right here, acting on every area within this gas. It's also acting at the interface. Once again, continuous liquid from what we learned in class. So this is the same area right here, or same pressure. So the pressure is going to be this hydrostatic contribution, which is Y again, as we called it, and this P naught term. So pressure 2 then is equal to rho Gy plus P naught, or PATM. P naught L is equal to rho Gy plus PATM times Y. So there we go. That's all it is to it. What you can do then is solve for any one of these variables and plug it into the other equation. What I would do is I think I would solve for y here. Y equals all kinds of stuff as a function of FA. And then plug y into there. And you'll have FA terms popping out. You'll end up with a square, a quadratic. It's pretty much just math from here. If you have any more questions, please feel free to reach out to me via email or during my office hours on Monday. Take care.